So this is going to be section 6.3 on proving parallelograms. In the previous section, we had properties of parallelograms. If you knew something was a parallelogram, we know that these things are true. Now, going really with the converse of that, how can we prove something is a parallelogram? Right now, we have the definition of parallelogram. If both pairs of opposite sides are parallel, then the shape is a parallelogram. There's going to be 4 other ways to prove something is a parallelogram. The first one we're going to talk about is this one. If I have a quadrilateral, and if I know that this segment is equal to this one, and I know that this segment is equal to this one, then if I know that, then I know the entire shape must be a parallelogram. This is another way that I can establish that I can prove deductively that something is a parallelogram. This is a theorem. We'll talk about the validity of why it works in a moment. But if both pairs of opposite sides are equal, then we have a parallelogram. This is one of my reasons for proof. If I'm looking for an example for this one, I could say that if my parallelogram is A, B, C, D, if I know this is a parallelogram, so whether I have the markings on it or I have in words A, B, C, D is a parallelogram, then my conclusion, back up, really messed that one up. If I know that this side equals this side, and I know that this side equals this side, then I could say that A, B, C, D is a parallelogram. So if I have both pairs of opposite sides equal, then I have a parallelogram. This is an example of how we could use this reason. We have acronym reasons. Sometimes we have names. This one, like if I want to use this in a proof, I would just say this. I just show these little diagram here. I could use words if I wanted to. I could say if both pairs of opposite sides are equal, then we have parallelogram. That's our second way to prove parallelogram after the definition. Next one. If I have a quadrilateral and these angles are equal and these angles are equal, then I know that the shape must be a parallelogram. So, definition of parallelogram. Number 2, if both pairs of opposite sides are equal, then parallelogram. This is number 3. If both pairs of opposite angles are equal, then we have a parallelogram. As far as how would I use this in a proof? Well, if I have a quadrilateral, again, I'll call it A, B, C, D. If I know that measure of angle D equals measure of angle B, measure of angle A is equal to measure of angle C, then I could conclude using this reason that A, B, C, D is a parallelogram. I can use the entire word parallelogram, or I can draw the little parallelogram symbol. Next one. If I have a quadrilateral, and I'm going to call this one, I'm actually going to give it the name to begin with, A, B, C, D. I'm going to draw in this diagonal. I'll also draw in that diagonal. If I know that AC and BD bisect each other, so if I know all of this, I have my drawing, I can see that AC and BD bisect each other, then I have a parallelogram. This is the converse of one of the properties we had before. We don't call it a biconditional. Biconditionals we save for definitions, but it does work both ways. If these diagonals bisect each other, then I know I have a parallelogram. As far as an example of using it, it's pretty much exactly what we have right here. If I wanted to change my letters, I could. E, F, G, H. If I know that FH and GE bisect each other, then I could conclude that EFGH is a parallelogram. And this is kind of a clunky one, in my opinion. It is helpful for solving problems, but for proofs, I don't like this one as much because notice I didn't put any symbols on here. I need to say that HF and GE bisect each other. If they bisected each other, that means that this would have been the midpoint. If this is the midpoint, that means that these little segments and these little segments are equal to each other. That would be true. But that's not how we have this one written, because trying to say that they share the same midpoint, or how we'd phrase that, is kind of hard to phrase. So I'll go ahead and give some of my opinions on this one, on these so far. This first reason is definitely a big 4-star reason. This is a great way to prove parallelogram. We like the equal. We like the segments. If you get both pairs of opposite sides equal, parallelogram, very useful for proof. The next one, both pairs of opposite angles equal to get parallelogram. This is either a 3-star or a 4-star. Again, this is just my opinion. It's helpful. Maybe not quite as helpful as the sides, but we do have equal, which is nice. It's better than having like words into our reason. So it is pretty useful. Whereas this one with the segments bisecting each other, these diagonals bisecting each other, is probably only a 2-star or maybe even a 1-star, because the whole idea of bisect is great, but trying to prove with bisect, we have all these little minute steps. Bisect leads to midpoint equals segments, and so forth. So a lot of definitions to be able to use this one. It's just not quite as convenient. For solving problems, it's nice, but for proof, it's not quite as convenient. All right, and I give this one more. So we have 4 so far. These 3 plus the definition of parallelogram, if you get both pairs of opposite sides parallel. And then here is our last one. If you have a quadrilateral and you get one pair of sides equal to each other, and if you also get that same pair of sides parallel to each other, then we know the shape is a parallelogram. So an example of how that would be used, go back to A, B, C, D again. If I know that DC is parallel to AB, if I know that DC is equal to AB, if I have all of those markings, then I could say, yes, ABCD is a parallelogram. So there's an example of how we would use this reason on a proof. As I mentioned in section 6.2, we have a lot of reasons for chapter 6 proofs. The first reasons we have are all properties. If we know something is a parallelogram, we can say these things to be true. These 4 new ones today are ways to prove something is a parallelogram. So I can establish something is a parallelogram. So there's a lot of different reasons. Some of these are just converses of each other. Am I trying to get parallelogram, or do I already know parallelogram? So of these 4 ways, these are theorems that I believe to be true, ways to prove something is a parallelogram. We're not going to prove all 4 of them. Of the 4, this last one is the one that's the most interesting to me. It combines both parallel and equal. This would be another 4-star reason. Parallel is not too hard to get. It's nice convenience. Equal segments, nice to use. So this is a very significant one that we like to use quite a bit. If I can get one pair of sides parallel and equal, parallelogram, and we are going to prove that. I know it says make an argument. Some of these notes are from the years of COVID where we loosened up on what proofs look like a little bit. We're trying to prove this theorem. If you have one pair of sides that are parallel and equal, then we have parallelogram. That's what we're going to try to prove. We're doing all of our geometry. If we want to use a theorem, we need to prove it. And we're not going to prove all 4 of those because the proofs get kind of similar. But let's see if we can prove this one. To prove a theorem, we need to come up with the given, the prove, a drawing, and then the proof. So I'm going to put my drawing over here. And we need to name this parallelogram. I'm going to name it, how about QUEN? What am I given in this one? Well, if I'm trying to prove this theorem, I have one pair of sides that are parallel and equal. I'm going to say, given that NE is equal to, I could say QU. I'm going to call it UQ because I can kind of see how this is going to work out with proving and so forth. So I know that these sides are equal to each other, and those same two sides are parallel to each other. So this satisfies the hypothesis. If we have one pair of sides like those that are both parallel and equal, then what we're trying to do is prove that QUEN is a parallelogram. So here's the given, here's the proof, there's the drawing. Now we have the proof to do. Should we claim the given? And already I feel kind of stuck. Like, how am I going to make this work? Think back to some of the proofs we did before. Use the given. I don't see how exactly I can use that yet. Keep the proof statement in mind. Find a way to combine given and prove. Then we go on some other tactics. Are there any temporary variables? No, not really. But another tactic we've used before is to draw in an auxiliary segment. The auxiliary segment we drew before was a diagonal, so we're just going to pick one. It doesn't matter which one. I'll go ahead and go with segment QU. I'm going to draw that in there. I don't have to say anything about it in my actual proof, but now I'm going to start using it. Because the top and bottom are parallel to each other, we have parallel, transversal, parallel. That means that we have some angles that are equal to each other. You can name them whatever angle numbers that you want. I'm just going to go with the very simple 1 and 2. Using PIAIE. That parallel implies that alternate interior angles are equal. We know measure of angle 1 is equal to measure of angle 2. These angles are equal to each other. I'm going to slow down and pause here a little bit. See if you can work in front of me a little bit. Can you get an idea of how this is going to start working out? By drawing that diagonal, we now have two triangles. Can we get those triangles congruent to each other? In other words, they share this side down the middle, and the way things are wrapping around, that is a symmetric. So with symmetric, we know QE is equal to EQ. Great. And then looking at those two triangles, the top triangle has a side angle side. The bottom triangle has a side angle side. So using side angle side, we may say triangle QEN is congruent to EQU. Great, the triangles are congruent. Maybe you could have anticipated that was going to happen, but we're still trying to get this shape as a parallelogram. And the most basic way to get that a shape as a parallelogram is the definition. Like, that's the only one I know for sure to be true. These other ones are theorems. I haven't proved them yet. But this one, can I get this to be a parallelogram by the definition? The definition is that both pairs of opposite sides are parallel. Top and bottom are already parallel. That was in our given. Can we get the left and the right parallel to each other? Think about the significance of having these triangles congruent to each other and how that's going to help us get these left and right sides parallel to each other. How about if I put an angle 3 right here and an angle 4 right there? Wouldn't those angles be congruent to each other? And because they're congruent to each other, wouldn't they then be equal to each other? If they're equal to each other, do you see how we can get parallel? So see if you can start working ahead a little bit on this one. So we get angles 3 and 4 congruent, then equal. Once they're equal, we can use AIEP. So this sentence right here combines two simple steps. I said definition of congruent angles. I never wrote that measure of 3 equals measure of 4, but I think it's a simple step. It's connected to the one before it. If 3 equals 4, then we have AIEP. We have to get them converted to equal first, and that's what I'm saying with this part. If I didn't use the AI or the definition of congruent angles, I don't have AICP, it's AIEP. That allows us to get that these two sides are equal, or excuse me, parallel to each other. So the alternate interior angles equal gives us the segments parallel. Now, as I look at this, the top and bottom are parallel, the left and right are parallel. That's good news. So we can go down to the conclusion. Applying the definition of parallelogram, we can conclude that QUEN is a parallelogram.